Welcome. In this video I'm going to try to explain what significance is, or specifically statistical significance, also known as a p-value. The definition of statistical significance is a little bit tricky and long at first. It's the probability of a result as in the sample, or even more extreme if the assumption about the population is true. So there are a few terms in here like sample and population that I've already discussed in another video. But still, even if you know those, this definition might seem a little bit daunting at the beginning. Note though that significance is therefore always a probability, so it's like a chance. To illustrate what this actually means and how it works, I'll be using a small example. Let's use flipping a coin as an example. I have coin A and coin B. Each of these coins I actually flip 200 times. Now coin A lands 92 times on heads and 108 times therefore on tails. While with coin B the outcome is 190 times head and 10 times tail. Would coin A actually be fair? If people look at these results, most people would think, yeah, that seems about fair. So yes, probably coin A is a fair coin. A fair coin indicates that the chance of heads and tails is equal. With coin B, if we ask the same question, a lot more people will start to doubt. So we might actually even think that the coin might not be fair. How this reasoning is done is actually a nice way to show what significance actually is. So let's break down the reasoning for this. For the reasoning, we begin with that if a coin is fair and we would throw it an infinite amount of times, we should have an equal number of heads and tails. The chance for a head is therefore 0.5, or as a percentage 50%. So if we throw a fair coin 200 times, we would expect around 50% times head, so about 100 times. Note, because we only limit ourselves to 200 times and not infinite, it won't be, or it's probably not going to be exactly 50% of the time. A small deviation is therefore expected, for a small deviation of this 100. But a large deviation from this 100 is not so likely. So with coin B, we had a deviation of, well, we had 190 times heads, I think. So that's a deviation of 90 from the expected 100. And for coin A, this deviation is only 8. So most people would consider 90 to be a large deviation, especially if we only throw 200 times, and 8 a small one. And looking at that, since we said that a large deviation is unlikely to occur if the coin would be fair, and a small deviation is likely to occur, so therefore most people would consider coin B to be unfair. So if you look at the bottom here, I have partially the definition of a significance, the probability of something if the something is true. So we're going to work out our previous reasoning and fill this in further. So I started with throwing the coin an infinite amount of times. That was at point 1 in the previous slide. That would be the population. And the assumption about this population is that in this example was that the coin is fair. So the assumption about the population is what we also seen in the definition. Then the deviations of 90 and 8 are each actually a result as in the sample. So these are the results as in the sample. So that was also in our definition. And the chance for a deviation of exactly 90 or exactly 8 are actually both quite low. But the chance for a deviation of 8 or more is a lot higher than the chance for a deviation of 90 or more. So the difference here is in the exactly 90 or exactly 8. Both are actually the chances of exactly that is extremely low. But if we look at 8 or more, so even a higher deviation than 8 or a higher deviation than 90, the chances become different. So for 8 or more, we have a quite big chance because it even includes the 90 or more. So this is actually what is then meant with that or even more extreme in the definition. So there we have that or even more extreme, and now we have finalized our entire definition of significance, the probability of a result as in the sample, or even more extreme if the assumption about the population is true. So getting back to our example, the probability for a deviation of 90 or more in a sample, if the coin is actually fair, is almost 0%. It's extremely low. This probability can be calculated. It's actually using a binomial probability, but that's besides the point for explaining significance in general. How the significance is calculated depends on each different situation. The probability for a deviation of 8 or more in a sample, if that coin is fair, is a lot higher, is 30%. So note that a deviation of 90 or more is not impossible. It will never actually be 0%. There is a very, very, very small chance that that coin is still actually fair and still have a deviation of 90 or more. So if that significance, that chance, that 0% or the 30%, if that is very low, then we either have a very rare sample or the assumption about the population is incorrect. Now the conventions to infer that assumption is incorrect if the significance is less than 5%. So if the chance of such a result, or even more extreme, is less than 5%, most cases we will then so-called reject the null hypothesis, the assumption about the population, and might consider it to be incorrect. This 5% is a bit arbitrary. There's a long debate about it, and some conventions are to use 1% or 10%, but 5% is still the most commonly used version of this. Of course, we might be taking that wrong decision, and these are then known as type 1 and type 2 errors, because we can make the wrong decision in two different ways. A type 1 error is if we assume the assumption is not true, while it is actually true. So in this case, we would assume that the coin is unfair, even though it's actually fair. This would happen in the case where we had that deviation of 90 or even more, and we would therefore conclude that the coin is probably not fair, if in fact that was actually a fair coin. We can also make an error the other way around. We could assume that the assumption is true about the population while it's actually false. So if with the other coin where we only had a deviation of 8, so the chance of a deviation of 8 or more was very high, so therefore we would say that the coin is probably fair. But it might actually be still an unfair coin. So in that case we have a type 2 error. I briefly mentioned this earlier, but the assumption about the population is sometimes known as the null hypothesis. That's what you assume to be true in the population, but should always be formulated in such a way that things are either equal or that there's no difference. So statistics from that perspective is very fair. And then we can either reject the assumption, and that's usually done if that significance is below 0.05. Now be careful that it's 0.5, and usually this first 0 is actually not shown, so it will only show 0.05, and then usually it's shown with 3 decimal places. So 0.008 is actually below the 0.05. If it's above or equal, then we would say that we have insufficient evidence to actually reject it. We won't actually accept the null hypothesis, because it might be that if we would take a larger sample that there is a difference, or that things are not equal. So we can actually never really show that the null hypothesis is true. There are some newer techniques, Bayesian statistics come to mind, that are actually trying to also be able to say something about the null hypothesis, but that goes far beyond the scope of this course.